That seems to work well.
Okay.
So the next talk will be on optimizing decision-making in concolic execution using reinforcement learning. If I printed the correct paper?
Yes. Yeah.
Good.
Okay. So
The virtual floor is yours.
sorry.
If you have something, the virtual floor is yours. If you have something to present.
Okay.
Yes.
Tell me when you see the screen.
We see it.
Yeah. Okay.
And we hear you well. So
yeah. Thank you
good.
for the presentation. So my name is Ciprian Păduraru. I will make a short presentation about our work on how we optimize decision making for concolic execution by using reinforcement learning methods. I will start with what framework we use behind this, some state-of-the-art methods. Then I will present the novelty of our solutions using reinforcement learning, some evaluation, and future work ideas. So first, our open source framework called River, which you can find it at these addresses. It's a collection of fast testing tools guided by AI algorithms. You can also find our previous work in the field using genetic algorithms, recursive neural networks, and so on at these addresses, both papers and GitHubs. We are very open to collaboration. If you want to collaborate with us, please don't hesitate. It works at binary level, including normal devices and ARMs, mobile devices. It's cross-platform. Well, I have to say that maybe I don't know how many knows this difference, but I want to emphasize it here that we work at binary level too, and this is important because many of the tools that are researched nowadays are based on LLVM and requires recompilation or translation to an intermediate language. We don't require that thing. We don't require, or methods do not require for the test process to know anything about the code or the process behind. This is our architecture in the River 3.0. In the foundation layers, we use some open source tools in the field, state-of-the-art tools like Triton for dynamic tainting, Lief for binary loader, Capstone for disassembly. Also, we have some work in progress to evaluate all of our methods on LLVM, because sometimes it makes sense to move out from only binary data inputs. And yeah, this is our collection of current tools, like the input generator using recursive neural networks, the genetic guided fuzzing, which is more something like AFL, for example, or libfuzzer, but at binary level. It doesn't require recompilation or knowing about the source code. This is the concolic execution using the SAGE method. And this is the component that I will be talking about in this presentation, the concolic executor using reinforcement learning. So the state-of-the-art paper in the concolic execution for binary, this is the pseudocode of it, and what it does is to start with a dictionary of input seeds, and just spam the input, the program under test with inputs. It runs it, every input is executed symbolically. It obtains a path constraints where the jump instructions occurred, and then the algorithm needs to decide which basically which paths should be changed to get new inputs. And this paper, what this paper brings is the elimination of backtracking to using this bound variable here. And it also has a novelty regarding this scoring heuristic, which puts all the inputs in a work list and scores how important is each input by the number of basic blocks that is detected, the number of new basic blocks that is detected by running that input against the program under test. Of course, you can find more details in the paper, but this is the high level overview of the paper method. So an example extract from their paper is this, where there is a function that receives an input, and if the input, it starts with the text good, but if the input was the string bad, then it will go through all these branches, the counter would be incremented, and then it will abort. It will raise this exception here. So if you give this function the text good, then the method on the shown in the previous slide will just execute will find the bad input string on the last branch of execution, on the last it will be put last in the work list. So the question is if we can optimize this. And if you take a look at and profile such a tool of concolic execution, you'll find out that most of the time is spent on the SMT evaluation of the branch conditions. So the main idea is to do some speed up improvements, is to cut the number of the SMT evaluations that could get faster to the problematic states. And of course, the idea was also presented in the original paper, like you have to assign a score, a heuristic to the decisions that you take, which branch you want to inverse. And our novelty and the key contribution of the paper is to use reinforcement learning to implement that kind of scoring and the evaluation. So if we take a look at again at the tree of the concolic tree evaluated, you will see that considering that P0, P1, P2, and P3 are let's say the path constraints that would lead you in the end to the branch that caused the problems. If we assign scores to the actions that we take, for example, if we assign score A for moving from state P0 of the program to state P1, and this score would be higher than all the other branches, all the other decisions that we take at that point of the tree, then it will make a faster execution towards the area that we target, the instruction that would cause the problem. So the problem now translates to something like optimizing the score of the action. And this is similar to what we see in the reinforcement learning terminology. Why? Because we have the concept of state, which is the current execution path constraint obtained by symbolically running the program under test. Then the question is, what is the best decision or actions to take, which translates to this concolic execution, like which branch should I inverse first to get higher rewards. And by higher rewards, it is basically the goal that you have for testing, because you could have different goals when you do testing, fuzzing testing. And one simple example is the new number of basic blocks that you could find by changing a branch condition in a given path constraint state. So this translates to evaluate the state action value. Okay, it's a classic Q-learning thing. Okay, so the environment in our case is the program under test. When you submit a series of inputs, like I1, I2, IN, and so on, what we do is to preserve the state of the environment to get determinism, and they don't affect each other. So this is known in theory as the contextual bandits, because it has a state first. At each point, you see the path constraint that you obtain, and you know all the basic blocks that were found up to that point. So that's why it is a contextual problem. It's not a simple bandit problem. And then you have because the consecutive actions do not affect the state of the environment, we say that it is a bandits problem. So in more depth, the state is a concatenation of embeddings for the basic blocks found so far, the set of basic blocks found so far, and the path constraint that you evaluate currently. The action is a numeric value index between 0 and the length of the path constraint. Basically, you have to modify one of those paths to obtain a new input. And the reward, you will see on the next slides a few examples of rewards, but the most common ones and used in the state-of-the-art paper is the new basic blocks found by taking an action in the state. We have an episodic environment, which means that we train with multiple episodes and with online batches that are updating the model. So imagine that from a mathematic point of view, what we try to do here is to learn the value of actions given the states of the testing process relative to the user goals that defines the testing process. So this is the network architecture, where what we do is to consider this state, the current path constraint that we obtained from symbolically evaluated the program. This is the current set of basic blocks that we found so far. We have some embeddings layer using these. Here we use dense and an LSTM layer. Then we have a series of 2 dense layers. Then we concatenate the features, and in the end, we obtain the estimation from the model for the state and the action, given that this is the state. So open a value, a float value, which says, with this path constraint, if I modify the branch at this index, it will give me this value. And that float value is the priority in the work list of the new input. And how do we train this thing? So as I said, we gather online experiences by running the model against the program, obtaining new input, obtaining basically stairs of state actions and rewards. And then we use the mean squared error to compute what was the estimation value versus the reward that we obtained. And by optimizing the parameters to minimize this mean squared error, in the end, the model will learn how to put the weights on the features here to have better and better estimation over time. This is an example of a reward function that is implemented in GitHub. You can find it working very easily to try if you want. And the first target that we have in mind is to increase the code coverage in the shortest time possible. So the reward function that is implemented over here says that the reward of a state and an action given the next state obtained means the number of basic blocks that we obtain using the next state, the next input, the difference basically between the number of basic blocks found newly using the new input. Okay, it has two parameters, but this is more like a detail to control the parallelism of the problem. You can find more detail about this in our paper. But to give you a quick hint, if you will manage to get if you manage to get changes at the top of the tree or in the path constraint, that it will provide better parallelism over time, because you have more branches below that index to run from now on. So it depends how you weight the things. Then we have another function or another example of reward function that could increase the code coverage in some code spots. And by code spots, we mean here a collection of basic blocks that are known as very susceptible to issues. For example, think that you have some code areas that are very prone to problems, and you would like the fuzzing process each time to touch those areas because you know that they are prone, but they are hard to find. So you can write a formula like this for the reward function to make the fuzzing algorithm basically to look more for those chord spots, the set of chord spots that you set. Then we have another kind of reward function that we were thinking about, and to obtain the input that maximizes the execution time. So the question is, you ask the model, the fuzzing RL agent, to find the input that causes basically the maximum execution time, or one that is close to the maximum. And here the reward function, just to give you as a hint, because you can read it more in the paper, the reward function has to value how big is the new path versus the path that you obtained previously. So you take in a path, given a path constraint state, you take an action and you obtain another path constraint, let's say, next time with the new input. And the question is, how big is this path against this other path? Or how much time it took to execute that new path obtained using the new input, we minus the previous, what is the delta time. And imagine that you have a loop or a while, something that continuously loops to the program. Of course, it will try to move on continuously and to find you the inputs that are causing basically infinite loops, or as much as possible inside your program. And imagine that with our framework, what you do is you can write your own reward function. This is just a few examples that we were thinking from our previous knowledge in the field, but the user can write and weight his value as he wishes to obtain something, to obtain a model and to train a model that it's closer to the user's desired target of testing. And a quick word about the evaluation. First, we try to see how efficient is the estimation. And we took two open source programs like GitHub programs like an HTTP parser and the JSON parser. And we try to see if we train a model with our method, how fast does it reach 100 different blocks versus the previous Sage method and implementation that is also implemented and open sourced in our framework. And yeah, as you can see, we are a little bit better than the previous method, which means that we can find faster those 100 different blocks, the first 100 different blocks in the applications using the reinforcement learning trained agent. The next question, how efficient is, or because we are working at binary level and we consider the path constraints, and it might raise you something that, okay, but how efficient is a trained model previously on small code changes? And for this test, what we did is to take 3 different commits, code commits, with small code changes like 10, 50 lines modified between them on both applications under test. And we try to see how much time it needs to reach the same 100 different basic blocks. And again, if we trained with the previous model trained on the basic code before seeing the small code changes, the agent trained on the original build was still able to beat the Sage method on the concolic method without seeing with seeing those changes. So what this means is that the policy that was initially working for the base code is still able to make good results on the modified source code with small source code changes. And why this is important? This is important because we might not have time, and this is costly, to retrain the model each time. If we could use, for example, imagine that you have a company and the programmers are submitting continuously code. You don't have time to modify the source code to retrain the model between those small smoke tests that you want to do. But what you can do is to use the previous trained policy for the reinforcement learning agent that is trained, let's say, nightly. So it would still get good results. We also try to see how it works on with bigger code changes, like take 1 year difference between the applications and the GitHub. Of course, the results were a little bit better, were on our side, but not so impressive, at least not on the JSON parser. But the results are still showing that the policy is transferable between code versions, and this is very important. This is important because the neural network succeeds to map the approximation function that we use for the neural network. It succeeds to find a good approximation and to keep to keep the same a good policy between versions. And we explain a few motivations that we're thinking that is happening behind the process. Some of the drawbacks is that training takes time and resources. The results that we showed you on the previous slide were trained using a strong GPU on 24 hours. And another drawback is that the model needs calibration depending on the application under test. So it means that you will have to put different parameters for, let's say you are a developer of application that is a text-based or an image-based, something like that. So it just needs different parameters for training. We will try to investigate if we could find some clusters of applications and that could somehow could get us a predefined set of, let's say, optimal parameters for the users for both training and inference. As future work, I think that as a conclusion, the reinforcement learning techniques for concolic execution are looking promising, and we could try to to move on and to investigate further this kind of techniques, like trying different algorithms to see to adapt to other types of problems and applications, for example, for IoT and cloud, where the problem is more complex, or and of course to move to standalone software that should retain its states between the inputs. It's not like you send it an input, it gives you an output, and then you reset the state of the program. The program stays there, you give it the inputs, you modify the state. Maybe after 100 different inputs, it will crash. Okay, thank you for your attention. We have some code snippets that are relevant for you, but you can also find them in the in the paper. However, the presentation is on GitHub. Please don't hesitate to collaborate with us if you want. Maybe we can open a new discussions based on this. Okay, thank you very much for attention again. And if you have any kind of questions.
Thanks for the presentation. Any questions?
I would have a question. So you mentioned that you train, you train against the program, and then you could do for regression when you make small changes. Did you also consider that in a certain domain programs have a similar shape? Yeah. So could it also be that you train one instance of a class of programs and get better results? Like, for example, I don't know, reactive programs always have this outer loop, and then they do the next state calculation when you generate, for example, code from Simulink. Yeah, there might be. Do you think this would work? That you get better heuristics for classes of programs?
Yes, that should be an interesting point of research going forward.
Or certain compilers, yeah, they might have compilers for a language might have different, similar behavior,
yeah.
Because you have the same grammar.
Yeah.
In compiler testing, for example.
Mm-hmm. Yeah, you're right.
Then maybe a question from me. Do you know of any heuristics or any other work that uses heuristics instead of reinforcement learning? Because I know that if we do model checking, simply doing a random breadth first search usually yields so much better results than regular breadth first.
Yes, there are a lot of heuristic in the field of fuzzing. Yes, and we evaluated some others. The point is I feel like the reinforcement learning is the way to go. This is my opinion, at least, because it in the long run it can be the hard-written heuristics. The only problem that remains in the field, from my point of view, is if the policies are transferable or not between the applications. And because if you have an application that you develop on your side and you try to use this kind of mechanism, it will work. But if you take that policy, that agent learned, and move it to another kind of application, it might not work. This is one of the biggest problems. And of course, the other problem that we investigated is the training time against the utility. Because if you have a program that changes very quickly, the policy that you trained in the morning might be not good when you finish the day. If you have like 1,000 of programmers, for example, and everybody submits something on one day on the application, the agent that you trained in the morning might be not good enough to get you good results overnight. And retraining might cost more than the whole thing. So these are some topics that need to be addressed. But overall, if you are trying to to just do. Maybe it would work to have like a combination of those kind of. I'm thinking now maybe we could combine the heuristics and the reinforcement learning agent, like to have
you learn when you use which one. Yeah.
Yeah.
So you have the meta learning.
Yes, exactly, meta learning.
Yeah. Yeah, very interesting. But because of course the heuristics have been learned, yeah, but they have been learned for the general, for the general models, and I think it would be very interesting. What are the heuristics, or what is the strategy? And that is what reinforcement learning gives you for certain shapes of programs. Yeah.
Yeah.
So it's kind of domain specific. Yeah, maybe.
Yeah, exactly.
So or an evolution, as you pointed out. Yeah. Or variants of a product, yeah. So all they have the similarities. So very interesting work. Yeah. And of course, it can be also used. I mean, the general approach could be, of course, also used for model-based test case generation. Yeah. If you have an abstract description of what the system should do, if you're a completely black box testing a server, for example, one could have a description or a model gathered through, I don't know, crawling a user interface like we've seen in the morning, yeah, and then trying to apply these techniques. Very interesting.
Good.
I was also wondering, maybe I have another question. I was also wondering, of course, you optimize for quickly covering a large number of blocks. Is there a danger that you miss then rarely executed blocks? So there are...
No, so we don't ignore a block. So the difference from the SAGE method here, for example, which consider all the blocks because they put in the work list all the possible paths of the program.
Mm-hmm.
We do the same, but we score it differently using the RL. So we don't lose any possibility.
It's just the order. It's just the order.
Yeah.
Yeah. I see. I mean, it was then just maybe this experiment where I said I want to, how quickly can I reach 100 different blocks, and the 100 were not all the blocks, I guess. Yeah, so
yeah.
Very optimized for this speed, but in general, you have full coverage.
Yes, I have full coverage. Yeah.
With the second colleague approach. Yeah. Mm-hmm. Yeah. Thank you.
Good. Then thank you again for the presentation.
Thank you for your attention. Yeah.
I guess that was it for this session. So I hand over to, I think, Bernhard for a few words.
Yeah, I think yes, we are at the end now, but after Amos is always before Amos. So I think we have we have also a next edition of